Hello, my name is Kyle from MASA-Dearborn, and today I'm going to be showing you how to pick out a battery for your application. So right here we have the battery that I picked, and I'll walk you through how I'm going to do that. So for MASA, we are doing a rocket, and on that rocket we have a bunch of different PCBs. What you're going to want to start by doing is making a current budget for your application. Basically what this does is just shows all your boards and how much current they're drawing at each voltage level, because on your board you're going to have buck converters, boost converters, and you're going to have different voltage levels. So right here, we have 1.8 volts, we have 3.3 volts, and we have 5 volts. For example, on the M2RB, which is the mixed range radio board, we're going to draw an average current on the 1.8 volt line of 1100 milliamps. Max current 1700 milliamps on startup. 3.3 volts, we're going to be drawing 559 milliamps and a max of 710 milliamps. And then on the 5 volt, we're going to be drawing nothing. Okay, so what you're going to want to do is you're going to want to add up each of these columns and you're going to want to put it in this post buck row. So I'll explain to you what this post buck and pre buck means in a second, but basically we just have all those added into there, all those added into there, boom, 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 all the way down. Okay, so post buck, that's the current that's coming out of the buck converter. In our case, we have a 7.4 volt battery, so we're only using buck converters because we don't need any like 12 volts or anything like that. So yeah, post-buck just says what's coming out of the buck converters, and pre-buck is what's going into the buck converters. And you'll see that they're different. The reason they're different is because power in is equal to power out. So you have voltage in times current in is equal to voltage out times current out. So using this fact, you can set up, and also we're ignoring efficiency of the buck converter, which is usually between 85 and 95%. You want to try to get like 90 to 95% for your bucks. That's just a note. Um, but the pre-buck, you set up the equation of V in times I in is equal to V out times I out. Yeah, V out times I out. And in this case, I out is going to be 1100 milliamps and I in is going to be 267 milliamps. And then, of course, your, oh, well, we don't know I in right now. We do know, okay, so we know I out, we know V out, and we know V in. So V in is going to be 7.2 or 7.44 volts. It depends on what the nominal voltage your battery cells are. We'll talk about that later. I out is going to be 1100 milliamps and V out is going to be 1.8 volts in this case. We're going with this column right here. So you set up the equation and then you do the math and you figure out that I in is equal to 267 milliamps. So you can see that from 267 milliamps, we get an output of 1100 milliamps, which is pretty cool. And then what you're going to want to do is you're going to want to do this for all of these. And then you're going to put the totals from your average columns or your average cells into this one and the totals from your max cells into this one. We're mostly just going to be using this average current draw because that's more representative of what's actually going to happen. This max current draw will be for a very short time on startup. And then what you can do is you have the total capacity of your battery, which is measured in milliamp hours. And our total capacity for our battery pack is 10,800 milliamp hours. So if you look at the units there, it's milliamps times hours. And so what you're going to want to do is you're going to want to divide that value by this total average current draw. And that's has a unit of milliamps as well. So you do milliamp hours divided by milliamps, and you're going to get hours for your unit. And that gives you a battery life of 3.3 hours for a battery. Okay, and all that being said, let's go and figure out how I picked out the battery. So this is the battery we have. The Samsung 36G 18650 3600 milliamp 10 amp battery. Right here, this title gives you two important statistics about the battery. Its capacity for just one cell right here is going to be 3600 milliamp hours. And its maximum continuous discharge current is going to be 10 amps. Okay. It has a nominal voltage of 3.6 volts, which is just about what you'll find for all of them. It's either 3.6 to 3.7 volts, somewhere in between. Um, and it has a maximum voltage of 4.2 volts. So these are important because for our application, we wanted a 7.4, 7.2 volt battery, something like that. So what we're going to want to do is we're going to want to put two of these batteries in series. If you put two batteries in series, the capacity stays the same, but the voltage goes up. So let's say you have two batteries In series, you have a 7.2 volt battery with a nominal capacity of 3600 milliamp hours. Okay, now you're going to copy and paste those two cells, right? You're going to copy and paste those 3 times, and then you're going to wire those 3 battery cells up in parallel. And so you're going to have 6 batteries, and in that battery pack, there's 3 cells, I guess you'd call them, which consist of 2 batteries, and then you wire those in parallel. And what you're going to get is from the 2 cells being in series, you're going to get a nominal voltage of 7.2 volts, a maximum voltage of 8.4 volts, and you're going to triple the nominal capacity by putting those three in parallel, and you're going to get 10,800 milliamp hours for your nominal capacity, your battery pack. And that's what we have here. We have the 10,800 milliamp hour battery pack with 7.4 volts nominal, and we have a battery life of 3.3 hours. 3.3 hours is fine for our application. The reason it could be a lot lower, we could probably get away with doing just 2 batteries, right? 7.4 volts, 3,600 milliamp hours, because we're doing a rocket and the rocket's very short. But the reason we have so much battery life is because well, the rocket's flight is very short. But the reason we have so much battery life is because there's always the risk of us getting stuck on the flight pad. So say that there's some technical error on the flight pad and we have to stay on the pad for like an hour or two. Maybe some other rocket has like liquid fuel and it's building up pressure or something, it's going to explode, and so you're not allowed to be on the pad. And so we're stuck there for 2 hours, let's just say. If we were to have a small battery with 1.1 hours battery life, like we'd have if we only had 2 batteries in series, our battery would die and none of our electronics would work. Um, but for our application, we run that risk, and so we want to have plenty of battery life, and that's kind of why we have that. Um, and by the way, the battery, it's 2 in series, 3 in parallel, and that'll be called a 2S3P battery. You can do this for everything. You can have like a 6S battery if you have 6 batteries in series, for example. You can have a 12S 20P battery if you want to get real big. Cars are huge. They have like high voltage lithium ion battery packs with ton of capacity. I don't even know what kind of numbers we're looking at for that. But yeah, basically you can scale this very highly, scale this concept. And that's pretty much all I have for you today, I think. I just kind of walked you through how to do a current budget and how to pick out a battery based on your specifications. Basically, you kind of want to weigh the benefits because like right here we have a 3600 milliamp hour battery. That's a pretty good capacity for a single cell. But the bigger your capacity, the bigger the battery is going to be. So you're going to want to work with the mechanical team and figure out how big that you can make the battery. And you're going to want to play with different batteries too, because perhaps if I picked a smaller battery, I could have put like 10 in series or something, or 10 in parallel or something, and that might end up being more nominal capacity than I would get from putting uh, 3 of these in parallel, you know? So you're going to want to work with the mechanical team, see how much, well, also if you run, well, no, that applies for batteries in series. If you run too many batteries in series, you're going to have to deal with complicated cell balancing. So I wouldn't recommend going too high with the batteries in series. You kind of gonna want to stick to between like 1 and 6 in series. I've seen ICs that are relatively simple that do 6 cell balancing, even 10. Uh, but yeah, for the dimensions and the capacity, there's kind of a trade-off there. The bigger the capacity, the bigger the dimensions, and the weight, of course. Okay, that's all I have for you. Sorry, I waffled on for a bit there, and I hope you have a good day. Goodbye.